The material we covered in section 3.1 generalizes naturally to higher order linear differential equations. In this video, we will discuss how a few concepts generalize. The definition of a homogeneous linear differential equation generalizes without issue from the second to the nth order case. A differential equation is homogeneous if the linear part of the differential equation is set equal to 0. Like so. Likewise, the superposition principle generalizes without issue. Theorem. Consider a homogeneous linear differential equation. If y sub 1 and y sub 2 are solutions, then so is c sub 1 y sub 1 plus c sub 2 y sub 2 for any constants c sub 1 and c sub 2. The existence and uniqueness theorem generalizes, although we need more initial conditions. Theorem. Consider a linear nth order differential equation where all these p's and this f are continuous on some common interval, and say we have initial conditions y of a equals a sub 1, y prime of a equals a sub 2, up to y n minus 1 of a equals a sub n minus 1, where this a is in the common interval of continuity. This has a unique solution. Linear independence requires a bit more effort. Consider a differential equation that has solutions y1 equals the sine of x and y2 equals the cosine of x. Then the superposition principle says we can form a third solution y3 equals the sine of x plus the cosine of x. Now, look at the collection of these solutions. The sine of x, the cosine of x, and the sine of x plus the cosine of x. None of these solutions are constant multiples of each other, but since this function was built from the other two, we certainly don't want to say that it's independent of them. To get at this idea, we need to modify our definition of linear dependence. Definition: functions f1 to fn are dependent if there are numbers a sub 1 to a sub n at least one of which is not 0. Such that a sub 1 f sub 1 plus a sub 2 f sub 2 to a sub n f sub n is identically the 0 function. We use this notation to emphasize that this is not an equation to be solved. We don't care if this is 0 at some value of x. We're asking whether it is the constant 0 function. Now that we have a definition of linear dependence and hence linear independence, we can generalize the idea of a general solution. Theorem: if an nth order linear homogeneous differential equation has n linearly independent solutions, y sub 1 to y sub n, then we can form a general solution c sub 1 y sub 1 plus c sub 2 y sub 2 to c sub n y sub n. Any other solution can be written in this form by selecting appropriate coefficients. In this video, we have seen how many definitions from section 3.1 generalize in a relatively straightforward way. In the next section, we will consider how to actually solve these linear higher order differential equations.